Hello everyone. In this episode we're going to talk about utility maximization and choice. If you remember our earlier discussion, we said we look at an individual's choice behavior, meaning we ask him or her a couple of questions about what would you pick if this set of available alternatives were this, and what would you pick if the set of alternatives was that. And given this declaration, we constructed a ranking, a binary relation among the alternatives, and basically we said if there exists a complete transitive and reflexive binary relation, well then, you know what, if we can construct such binary relation, well then we said actually we can rationalize the individual's choice behavior. And that rationalization, if you remember the notation, C is the choice behavior of the individual, and then let's say this is the preference relation we construct by looking at my individual's choice behavior, and then construct a sort of a robot, and that robot basically always maximizes this preference relation given the a choice set available to him. And we said, well, the choice behavior will be exactly identical to that robot's choice behavior. And so that was sort of the idea of rationalizing an individual's choice behavior. Well, and if you again remember the theorem we had, if the choice behavior of an individual satisfies condition alpha, well then we can always find such preference relation. And so meaning we can always rationalize this choice behavior of this consumer or individual. So what we assumed is basically in economics is that our individual, our decision makers, consumers or producers, whoever the individual decision makers are, they actually satisfy this condition alpha, meaning we can rationalize their choice behavior. Remember the arguments I made in the as-if approach? So even though we are unsure about the decision makers' intentions or, you know, actual and true preferences, we don't care about it. All we want to do is to find some preference relation that is going to be and construct this robot that is going to behave exactly identical to our consumer. So once we have a preference relation, we already know that we can represent this preference relation with some utility function. And so, therefore, I am not going to look at my consumer from this moment on. I am going to assume that my consumers can be represented by this preference relation or a utility function. And so I am going to look at the choice behavior of this robot. And this robot's choice behavior is simple because it always maximizes the preference relation or the utility function subject to the available set of alternatives, meaning subject to the constraint. So the behavior of this robot is therefore very simple. Maximize utility subject to the constraint, whatever the constraint you have, right? Constraint determines the set of available alternatives. So the last time we talked about the utilities defined over the Rn. So I am going to start with the simplest example where there are only two goods. All right. So that means my problem is the utility maximization problem, or the problem of this robot is maximize the utility function, which has two variables, let's call them x and y, by choosing x and y obviously are plus, so we don't want a negative consumption, subject to constraint. So, okay, so what is our constraint? Well, depending on the environment that you are analyzing, constraint can be different, right? But what we would like to do, we would like to construct a demand theory. And so the simplest model we have is, well, the constraint is basically the budget constraint, all right? And the budget constraint is very simple. Let me call it budget constraint. So it basically tells me the following: your expenditure cannot exceed your income. as simple as this. Well, what is income? Well, obviously, it may be very complicated. Your monthly salary, the dividend payments if you're working in two different jobs, and then another wage may be coming from there. Maybe your partner or maybe your partner is working, and so that also an additional income. So the income could be in reality, maybe you're earning an interest earnings, and so that also can be a part of income. But let's keep it simple so that your income is all right, just some income level. And well, what about your expenditure? So our framework is, well, we keep the framework as simple as possible. There are two goods in this economy, in this problem, and these goods are not free. Each good has a price. Price of good X and price of good Y. I assume that they are positive. Income is also positive. So therefore, your expenditure, if you buy X unit of good X, all right, this is how much money you need to spend for good X, and Y unit of good Y, this is how much money you're going to spend on good Y, has to be less than or equal to income, as simple as this. Well, clearly your expenditure can be more complicated in real life. Like, for example, I need to go to shopping, and so there's a transportation cost, this and that. Well, let's ignore all of this just to keep the model as simple as possible. All right, so basically this is what the budget set is, or budget constraint is. All right, well, let's draw the budget set or budget constraint, because we will keep doing it again and again. It's good to do it at least once in detail. So there are two goods, good X and good Y, and I would like to draw my budget line or budget set. So how do I do that? Well, very simple. We first actually look at the equality part of this relation, all right? So XPX, YPY is equal to income. Very well. Well, don't forget, the income is some real number. Y is some real number, positive. They're all positive. And X is also PX is also a real number, a positive real number. So here, the same PY, not Y. So here, the only choice variables are X and Y, all right? So we choose X and Y. So we can vary X and Y, but all the other parameters are fixed, all right? So like constant. So how do I draw a line like this? Well, very simple. When Y takes values of 0, right? So we are on the horizontal axis, X. So then X can be, so this is 0. X is therefore equal to income divided by PX. So let's say this is income divided by PX. All right. When X is 0, that means we are on the Y axis. So we are finding the Y intercept. Well, the Y has to be equal to income divided by P of Y. All right. Well, then you know what? This is a straight line. We know that. And so this straight line must connect these 2 points. So all the points on this line is basically satisfying this. You don't really need to go below here or beyond here, because I know that Y is negative and X is negative will never be in my choice set. So you don't really need to worry about all those parts. All right, but this is exactly what the budget line is. So this is what we call budget line. And remember, my constraint is inequality. So my expenditure must be less than or equal to income. So this line tells me my expenditure is equal to my income, and everything below it basically tells me that my expenditure is less than my income. Again, I ignore those negative parts simply because X and Y will never take negative values. So therefore, this triangle is what we call a budget set. Okay, so this maximization problem, maximize utility, the maximization problem of my robot, which represents my individual's choice behavior, all right? This maximization of utility subject to this constraint basically means, look, we have this triangle. I know everything on the first quadrant is allowed. So you can choose any one of those, but your constraint tells me that you have to choose a point in this triangle because everything outside of this triangle is way too expensive for you. You don't have this income, all right? So your income limits you to buy something in this set. Obviously, you can choose 0, 0, meaning consume nothing, right? Or you can choose something here on the boundary, meaning you spend your entire money, or somewhere here. That also means you spend your entire money. But you can buy different X and Y's in these two situations. So there are infinitely many possibilities, obviously. You can also buy something here. Question is, which one are you going to buy? All right. Well, that's a good question. There are different ways of solving this. So I am going to solve this sort of generic problem graphically first, and then I'm going to mathematically solve this. So don't forget, this is our setup, all right? Utility maximization subject to a constraint, and we have two goods. All right, so I'm going to draw this budget set again here. So I have a budget set, all right? So this is income divided by PX, I'm sorry. Income divided by PX, and the y-axis is always income divided by PY. This is x-axis, and this straight line is my budget set. Okay, so again, my optimum point has to be in this triangle, u of xy. I want to maximize it by choosing x and y subject to pxx plus pyy equals, less than or equal to income. Okay, so what is my utility function? Well, utility function, I can't draw it on this picture because to draw this two variable utility function, I need a three-dimensional space. But what I can draw here is the level sets or the indifference curves. All right, so I better use a different color, I guess. So here is the blue color. So this blue color is just one indifference curve, all right? But don't forget, there are like infinitely many indifference curves floating around my space, right? This is another indifference curve, and so on and so forth. And let's assume for now is that higher indifference curves, meaning as we move in this direction, means a higher utility level. So therefore, this indifference curve I star is giving this individual or robot higher utility than indifference curve I because it's lying above I. All right. So the thing is, for example, you can buy 0, 0, but that's going to give you probably zero utility. If you buy a bundle, this bundle, that will clearly give you higher utility because this indifference curve represents a utility level which is positive. But you know what? This point gives me even higher utility and it's still affordable. Why is it affordable? Because it's in this triangle, remember? So everything in this triangle or on the boundaries are feasible for me. Outside of it is not feasible. But you know what? Keep going this way. Well, for example, this point. Well, this point, interestingly, gives me exactly the same level of utility as the previous one, I mean this one, but it's more expensive because here I don't spend my entire money. How do I understand it? Well, everything, every point in this triangle actually satisfies pxx plus pyy strictly less than I. All right, and everything on this boundary in fact satisfies pxx plus pyy exactly equal to I. All right, and therefore if you are in the triangle, not on the boundary, I mean the budget curve, budget line, well that means you're not spending your entire money. But Graphically, first of all, there is another point here where exactly the same cost, meaning I spend my entire money, but it gives me higher utility because it's on a higher indifference curve. Well, you may wonder, how, well, yes, graphically that's obvious, right? Higher, this point is clearly on a higher indifference curve, so that means higher utility, but what is really the intuition behind this is like, I am spending my entire money, but for some reason I am getting higher utility. How so? Well, remember the marginal rate of substitution is like, maybe here you are consuming too much good X, but too little good Y. But, this is too much good X. And I think of this sort of standard example. This is, slice of pizza versus Coke that you want to drink. Well, here I am having like 8 slices of pizza. Boy, this is too much. 6 is even, fine, but I'm consuming 8 slices of pizza and very little Coke. But I actually want something, it's too dry. I want something, I want to drink more Coke or whatever juicy juice you want to drink. So therefore, in this sort of a different allocation, although the total amount of money you spend is the same, is a different bundle, all right? Different level of slice of pizza and Coke. So here, instead of consuming 8, you consume maybe 7 slices of pizza, but instead of a small Coke, you have a bigger Coke. You see what I mean? So different combinations can actually give you higher utility. So therefore, the point of optimality is finding the right balance between different alternatives, goods that you want to consume. So therefore, graphically, when we look at it, the optimal point has to be this guy. Well, why is that? Well, first of all, this is the highest indifference curve I can achieve, right? At least for 1, 2, 3, 4 blue indifference curve that I draw. All right. And to be honest, a higher indifference curve, higher than I star, is going to be lying beyond my budget set. All right. So any point on this higher indifference curve is going to be infeasible. They're way too expensive for me. So therefore, this is the highest indifference curve I can achieve. And second of all, it is affordable. That point is the only affordable point in this indifference curve, right? For example, this point is also giving me the higher indifference curve by just increasing the slices, decreasing my consumption of Coke. But the thing is, this is way too expensive, all right? I can't afford it, again, because it's outside of my budget set. So therefore, this point must be my optimal consumption. So that means the solution to this maximized utility subject to budget constraint, the answer has to be this point, all right? Very well, but what can I learn from this geometric observation? Well, kind of simple. If you look at this carefully, there are 2 curves that are tangent to each other, right? One curve is the indifference curve, and the other curve is the budget line. So what does tangency mean? If 2 curves are tangent to each other at some point, let's call this point X star, Y star, because they're starred, because they are the optimal. So at this point, tangency means the slope of these 2 curves are equal to each other. We know this from mathematics, right? Let me repeat. If 2 curves are tangent to each other at some point, that means their slopes at that point are, the slope of their tangent line passing at that point must be the same. So let me write it this way. Slope of the indifference curve is equal to slope of the budget line at point X star, Y star, because these 2 points are tangent to each other at exactly X star, Y star. Well, very good. What is the slope of the budget line? Well, simple. Remember, my budget line is xpx plus ypy equals income. And its slope is basically the y-axis, the y-intercept divided by the x-intercept, because the slope is always the tangency of this angle, all right, which is I over py divided by I over px, which basically means px over py. But there's one point that you must be careful about. It is minus. Why is that? Well, because this is a downward sloping curve, and so downward sloping lines or curves always have negative slopes. So therefore, the slope of the budget line is minus px over py. This is the price ratio, but it's minus. Very well. What about the slope of the indifference curve? Remember our arguments in marginal utility, marginal rate of substitution? There we said marginal rate of substitution is nothing but the slope of an indifference curve. All right, that's always true. So if you want to find the slope of an indifference curve, you have to calculate the marginal rate of substitution, which we did in our earlier lecture. It was minus del u divided by del x, del u divided by del y, meaning the marginal utility with respect to good x divided by marginal utility with respect to good y. Don't forget the minus sign. So the slope of the indifference curve is minus mux divided by muy, which is equal to this. So you know what? What I have is the following. This is MRS equals minus price ratio. So you probably remember this from your intermediate microeconomics courses. For a utility function, for a utility maximization problem in a two goods economy, the marginal rate of substitution must be equal to price ratio minus px over py. This is, by the way, necessary condition, meaning it's not sufficient. I mean, for some utility functions, this is not going to hold. So this is necessary, meaning this basically gives me a critical point, obviously, all right? Under certain conditions, right? For example, the utility function is, if the preferences are convex, all right, strictly convex, and a utility function is, continuous, differentiable, etc., etc. That can also be a sufficient condition, meaning any x star, y star satisfying this is definitely the optimal solution for this problem. However, when x star, y star satisfies this, it may not always be the optimal solution, all right? So you have to check the second order conditions. But most of the times given that utility functions are nice behaving, etc., we basically solve this equality and find those critical points x star, y star. All right, so let me write it again. The marginal rate of substitution, remember that depends on what x star and y star you plug in, has to be equal to minus px divided by py. So this is graphically how we end up this necessary condition. So what I will do next is looking at a more general framework having more than two goods, all right? But it's just a simple generalization. You can just assume the n is equal to 2, and so everything is going to work exactly the same way. And more importantly and different than this, we are going to actually mathematically solve this problem rather than drawing these graphs and come up with the necessary conditions. And the necessary conditions, you will see, is going to give us exactly the same thing. MRS has to be equal to price ratio. One point though, again, this is necessary condition, meaning that sometimes the optimal can be on the boundaries. The boundaries means the optimal solution is either here or here, for example. By the way, the optimal solution will never be on this boundary or on this boundary. By the way, when the optimal solution is on the budget line, except these 2 points, we call it interior solution. It's not interior in the sense that x star, y star is strictly positive, which means x star is positive, y star is positive, all right? So that means interior point. The boundary point means either x star, the optimal solution on the x dimension, or the y dimension. One of them is 0, all right? So that gives me the corner solution. So I am sorry, I sort of asked a question, posed a question, and did not answer. So I said our optimal solutions will not be in this region or in this region or inside this triangle. Why is that? Well, if the utility function is an increasing function, all right, it's an increase, meaning the more you consume, the happier you're going to get. Well, then, in this framework, money or anything else is not going to give you any utility, right? The only thing that gives you utility is good X and good Y consumption. Amount of income you will save is not going to give you utility. So in this very simple framework, if you realize there's no future, there's no tomorrow, so you have some money, $100 bill, all right, or $100 credit card, Amazon card, and the thing is you can buy either X or Y or both, depending on how much you like them. And then the thing is, once once this choice problem is finalized, the remaining credit in this card or remaining money that you have is going to be thrown away, all right? It's going to be a waste to not spend this money. So that's the framework. It's implicitly assumed in this framework, all right? Sometimes we may assume a utility function x, y, and m, where m is the residual income, meaning whatever you spend, I minus your expenditure could be the residual income, the money left. So if you get utility out of, so like holding money in your pocket is giving you extra utility. In that case, obviously things are going to be different. Maybe if I have time, I'll later do an example for this. But in this very simple framework, again, extra money is not going to give you any utility, which means you have to spend, if you're talking about an optimal choice, utility maximizing choice, well, you have to spend your entire money. So therefore, the optimal solution is going to be on the budget line, but optimal points can be on this boundary or on this boundary, meaning you prefer to spend your entire money on good X and no good Y, or the opposite, you spend your entire money on good Y and spend no X. In fact, probably not the next, but maybe 2 videos after this one, I am going to give solve different examples with different utility functions, and normally perfect substitute examples are always going to give me, almost always going to give me boundary solutions. All right?